Now, you got the idea what is nose temperature, what is its importance. So, nose temperature is a very important temperature which provide you a point whose temperature in case of a plain carbon steel is around 550 degrees centigrade, and this temperature generally provide you a point at which if we draw a tangent cooling curve from 723 degree centigrade to room temperature, then your final structure will be 100% martensite, but that martensitic structure will have less or minimum, you can say, initial stress and minimum distortion, because generally if you cooling rate further increase, then that also produce you martensitic structure there, but that martensitic structure generally will have higher initial stress or internal stress, and it will have higher distorted shape also. Okay, what I am telling, understand, this you should keep it in mind. Now, we are going to discuss about the dimensionless parameters which will be required to decide when we should use what is called equation for thermal history prediction. So, we have already got the idea about cooling rate in case of two dimensional case. The cooling rate we got as dT by dt, little bit I am writing, that is generally 2 pi k rho c g square v by q, okay, whole square T minus T0 whole q. This is for two dimensional case, and another equation also for three dimensional case I am just directly writing, that is generally called dt by dt is equal to minus 2 pi k v by q, 2 pi k v by q T minus T0 square. Okay. Now, from this equation what you can get from this is for three dimensional types of heat flow cooling rate equation, okay, which we got generally based on thick plate solution of thermal history, Rosenthal thick plate solution of the thermal history. Okay. Now, from this equation one things you can observe that in this equation generally the cooling rate is depends on thickness of the plate, but here you can see in this equation there is no thickness parameter. So, what you can say here, or here I am writing for a particular material, if your welding velocity, then what it is called heat input. What is heat input? It is generally net input, heat input, that is eta Vi in watt, its unit is watt, always you should keep this thing on it. What is V? V is welding voltage, I is welding current, and if your velocity, welding velocity, let us meter per minute or millimeter per second, whatever it is, okay. If this things is constant for a welding process, you can say this, and another things, if your actual temperature T and T0 is also, let us, if it is a for a particular temperature T, let us this actual temperature, generally for cooling rate calculation for a welded specimen, this T actual, or you can say T, which you consider, here I am writing T A. So, this T A generally is considered as nose temperature, always you should keep it in mind, nose temperature generally for cooling rate calculation. Why? I will discuss in subsequent slide, that is 550 degree centigrade temperature, because this is a critical point, that is why we used to consider for cooling rate this critical temperature. Okay. Now, I will discuss this thing. So, for a particular temperature, particular what it is called Q and V as well as K value, you can say this right side of this three dimensional heat flow equation is, this is generally you can say is constant. This right side equation is, right side of this equation is constant. Now, if we just make it the ratio, that means dimensional analysis for this equation, dt by dt divided by minus 2 pi k V by q T minus T0, then what happens, what should be its value? Its value will be exactly 1, correct. If all other parameters are constant, then its value is coming as 1, correct, this ratio. Now, this is generally called dimensionless cooling rate, as it is unitless, that is why it is called dimensionless cooling rate, you can say, for 3-dimensional heat flow, 3D heat flow. So, in case of 2-dimensional case, based on this equation, what you can get? You can get 2 pi k rho c g square v by q whole square t minus t 0 to the power q divided by, what are the other things we got? Minus from 2 pi k, because these are, if these are constant, 2 pi k v by q t minus t 0 whole square, correct. These are the things we can get from this equation in case of 2-dimensional case. So, what are the dimensionless parameter from this equation we are getting? How it is coming, you got the idea. That means, in this dt by dt I put this 2-dimensional types of cooling rate, then we are getting a very interesting ratio. This is also dimensionless, this is also dimensionless, correct, this is also dimensionless, this you should keep it in mind. Now, I am just doing some calculation from here, what we will get. So, we will get this 2 pi cancel, you can see this, so 2 pi k cancel, v by q, this v by q cancel. So, what are the things we are getting? G square rho c, and another terms is there, that is generally v by q, okay, and t minus t 0. Okay. These are the thing generally we got, correct. So, this is also dimensionless, this is also dimensionless. So, this I am representing in terms of a, you see, it is a function of g square, thickness square. So, here I am writing this is a dimensionless what it is called thickness, that I am representing in terms of a g bar square, because as this here we are discussing about dimensionless thickness, and as 2-dimensional cooling rate is a function of g square, and as we are getting a equation which is a function of g square, that means cooling rate ratio is a function of g square. That is why here we are representing this left side term into g bar square. This is called dimensionless thickness, dimensionless thickness, this you should keep it in mind. This dimensionless thickness g bar square is actually we are getting in case of what is called 2-dimensional case. So, what is g? You can write, so the dimensionless thickness you can write as thickness of the plate into rho c v by q t minus t 0. This you should keep it in mind. Whatever the dimensionless thickness you are getting a square, this second equation is called dimensionless cooling rate for 2-dimensional case. This is called dimensionless cooling rate for 2-dimensional case. So, here I am drawing this cooling rate in terms of the ratio of the cooling rate plus g. So, let us consider this is your g bar and this is your the ratio of this dt by dt divided by minus 2 pi k v by q t minus t 0 square. Okay. This ratio, let this is your y, this is your y, and this is your G bar. So, what you observe, this ratio in case of 3 dimensional case, you see this y equal to generally 1. So, what you got, y, let this is your 1. So, y equal to 1, this is generally for 3 dimensional case, it is a constant value. So, for any value of G bar, you can say this y, this ratio is, you can say, equal to 1. Whereas, in case of 2 dimensional case, this ratio become, in case of 2 dimensional case, what you are getting from this equation? You can say from this equation become y is equal to your G bar square, y equal to your G bar square. What is this equation? This is the equation of parabola, correct? This is the equation of parabola, you know these things. So, if we draw in case of 2 dimensional case, how the parabola of the dimensionless cooling rate you are getting, parabola of dimensionless cooling rate curve, how you are getting. So, this is generally called, you can say this is generally called y equal to G bar square. Okay. Now, always you should keep it in mind, this 3 dimensional types of cooling, non dimensional cooling rate, it has a constant value. So, this y equal to G bar square, which is the cooling rate curve for, this is for 3 dimensional types of, this is this equation for 3 dimensional type of cooling rate equation. Now, from this equation, one thing you can observe, where this 2 dimensional and 3 dimensional curve was crossing. So, left side of this curve is called generally your 2 dimensional types of cooling rate equation will be valid in this zone, and from this crossing point, the right side zone generally is considered as 3 dimensional types of cooling rate is generally valid for this zone. So, if a G bar value, that means for a particular of welding operation, if your G bar value, you can say greater than 1, you can say, then you can consider that zone is coming as, considered as 3 dimensional types of heat flow, and if this G bar value is less than 1, you can say there you can consider 2 dimensional types of heat flow. Now, here generally a very interesting types of region we can define, that is called transition zone. This transition zone is defined here, I am defining, is a zone where generally G bar value is varying from 0.9 to 1.2, what I am telling, understand, this transition zone. In this transition zone, where generally your heat flow is in between 3 dimensional and 2 dimensional types of analysis. That is why this G bar value will be considered for 2 dimensional case generally. Here I have shown a general thing, but once you impose this transition phenomena, there generally you can say if the G bar value is, you can say, less than equal to 0.9, there generally you can consider 2 dimensional types of heat flow, and G bar value if it is greater than equal to 1.2, there generally you can consider 3 dimensional types of heat flow equation. This you should keep it in mind. So, how this G bar is dependent? This G bar is dependent on this parameter I have already shown. G bar is equal to G into square root of rho C V by Q T minus T 0. So, this dimension, based on this dimensionless parameter, you can define which case you should consider 2 dimensional types of heat flow, which case you should consider 3 dimensional types of heat flow. So, where you should use 2 dimensional types of heat flow equation, where you should use 3 dimensional types of heat flow equation, and where you should use 2 dimensional types of cooling rate, and where you should use 3 dimensional types of cooling rate equation. These are the things you can get the idea from this dimensionless thickness parameter. This you should keep it in mind. So, what you observe, the transition zone, if this transition is zone, generally in this transition zone, if it is crossing the point 1, that means if it is crossing the g bar value 1, then you can consider their 3 dimensional equation is more accurate. If it is left side of this g bar point 1, there you can consider generally 2 dimensional types of heat flow equation. This is called transition zone, this you should keep it in mind. So, this transition general zone, why it is considering, because in this zone you can use either 2 dimensional types of heat flow equation or 3 dimensional types of heat flow equation, this you should keep it in mind. Now, just before sometimes whatever the parameter I have shown, like for submerged arc welding, generally I have shown that for a 50 millimeter thick plate, that means 50 millimeter G value with a current of 900 ampere, voltage of 27 volt, then welding speed of 0.2 meter per minute. By using the above equation, your 7850 kg per meter cube, and your T actual, that is which we are considering, which is actually your nose temperature 550 degree centigrade, its give us, and room temperature T 0 equal to 25 degree centigrade, it give us a G bar value which is equal to your 0.88. You can calculate this thing. So, which is generally this less than, you can say 0.9. So, as it is less than 0.9, so directly it is a phenomena of 2 dimensional types of heat flow. That means, here the heat flow is parallel to surface of the plate, there is not 3 dimensional types of heat flow types of equation. So, in this case you should use what types of heat flow equation, that is 2 dimensional types of heat flow equation I have already derived, that is generally called based on line heat source, whatever the equation you got, that equation you should use in this case. Whereas, in case of a mag welding process, I have already shown you, there the parameter also I have shown for G is equal to 20 millimeter thick plate, current of 150 ampere, voltage of the voltage was I have already shown, what was the voltage in previous slide I have already shown, voltage of 20 volt. That means, for mag welding process G equal to 20 millimeter, I equal to 150 ampere and V equal to 20 volt, where the welding speed is 0.4 meter per minute, and keeping all other parameter this with a efficiency, let us here with a efficiency of 0.8, here we got the G bar value which is equal to 1.28, what I am telling you, you can calculate this thing also. So, which shows us a 3 dimensional types of heat flow. So, though the thickness here is less than 50, then also you are getting the heat flow patterns different. That means, it is not only depends on your thickness of the plate, it is also depends on these parameters used in the welding process. This you should keep it in mind. Okay. Now, we will discuss about a problem which is related to this cooling rate calculation. Then after that directly we will go to discuss about the peak temperature achieved in this welding process. Now, the statement of the problem is like the welding parameter used for a butt welding operation of 6 millimeter thick steel plate, that means, here G is given as 6 millimeter. Here welding parameter used is welding current is 300 ampere. So, I is given as 300 ampere. Welding voltage V is given as 25 volt, and welding transverse speed, here welding transverse speed that means V, small v is given as 8 millimeter per second. The thermophysical property that means here rho C, multiplication of rho into C, which is given at 0.0044 joule per meter cube Kelvin. Okay. And your conductivity, thermal conductivity K is given as 50 watt per meter Kelvin. These are the parameter you can see. Actual temperature is given as, so is the nose temperature, that is 550 degree centigrade temperature we generally used to consider. If the initial temperature is, so here T0 also is given as 25 degree centigrade temperature, then find the cooling rate. So, you need to find what should be the cooling rate. So, by using this parameter you need to calculate the cooling rate, but so here what you do not know whether you should use 3-dimensional types of equation of cooling rate or 2-dimensional types of equation of cooling rate, that you do not know. So, for calculating this, generally first of all what you need to do? You need to first calculate your what? Dimensionless thickness. What is the equation of dimensionless thickness? So, dimensionless thickness G bar you know is equal to your thickness of the plate into a square root of rho C V by Q T minus T0, correct. These are the equation you know. Okay. So, by putting everything you know, G is 6 millimeter, rho C is given as this, V is given as 8 millimeter per second, Q is generally calculated. How to calculate this Q value? Q generally calculated is net heat input is equal to your eta Vi. This you should keep it in mind. So, what is eta? Eta is given as, what is the thermal efficiency here? It is given, the thermal efficiency is given as 0.9. So, let us here consider the thermal efficiency is 0.9. So, here eta is equal to let us 0.9. So, for 0.9 thermal efficiency, voltage is given as 25 volt, current is given as 300 ampere. So, this will give you Q value. So, this Q value you put here, your T is actually T actual, this is actually your 550 degree centigrade and this actually 550 degree centigrade here you can say 550 and this T0 equal to you can say 25. Okay. So, by putting all these value you will get a G bar value which is equal to, directly I am writing these things, which is equal to your 0.3139, it is 0.3139. Okay. So, this is a value which is less than equal to you can say 0.9. So, as it is less than equal to 0.9, so which cooling rate equation now you need to use? So, here you need to use the cooling rate equation which is actually 2-dimensional types of cooling rate equation. So, here what are the equation you need to use here, because this is, so here what types of heat flow are there? This is a 2-dimensional types of heat flow, 2-dimensional heat flow. So, here, so the for cooling rate calculation, so the cooling rate calculation we need to use 2-dimensional types of cooling rate equation. So, the cooling rate of this process will be what? Dt by dt, this here you need to use whatever the equation you got for 2-dimensional case, that is generally 2 pi k rho C G square V by Q whole square T minus T0 to the power whole q. This you should keep it in mind. So, by this generally you can directly find out what is the cooling rate of your equation, that is actually equal to your 10.1149 degree centigrade per second. So, per second this much of temperature will reduce. What I am telling, understand? This is the cooling rate. So, by using this time, that means cooling rate, you can easily predict what should be your final microstructure by using TTT diagram. What I am telling, understand? So, this is one problem. Similar types of different types of problem can be there. Based on this thing, you can easily find out what is the cooling rate of your. So, one of the problem generally here I solve. Now, we will discuss about the concept of what it is called peak temperature. This is a very interesting phenomena. Now, based on this two dimensional types of heat equation and three dimensional types of heat equation, you can again be able to calculate what is the peak temperature of a particular location achieved during the entire welding process. What does it means, peak temperature? So, now we are going to discuss about the peak temperature. So, what is peak temperature of a welding process, or what is peak temperature of a point of a welding process? Little bit I am just discussing. Let us consider this is a plate, this is subjected to a welding operation, this is the welding line. This is the welding line. Welding line, or you can say let this is the fusion line. Here the fusion is taken place, let this is fusion line. What is fusion zone? Fusion zone means the zone where the temperature crosses is melting point temperature. So, generally peak temperature means at a particular distance, let us at a particular distance from the weld center line, let this is your y, at a particular distance y from the weld center line, what is the temperature it achieved during the entire welding process, what is the maximum temperature it achieved during the whole welding operation, that is generally called T peak temperature of that point. So, you see you can say from the center line of a particular distance, then only peak temperature achieved throughout its entire welding process. These are the point generally have same distance for a particular distance y throughout the entire welding process, that distance generally can achieve a temperature which is the same temperature. What I am telling, understand? This is the same temperature. Now, what is the temperature it achieved for a particular point from the weld center line? That thing is derived by a person whose name is S. Murugan. Okay. He is a researcher who generally find out this peak temperature by solving the equation of thin plate solution of Rosenthal equation and thick plate solution of Rosenthal equation. What I am telling, understand? So, by solving that thin plate solution of equation for line types of heat source, he got the peak temperature equation, which is looks like, I am just directly writing this equation, Tp minus T0 1 by Tp minus T0 equal to square root of 2 pi into E divided by Q rho C here I am writing C square root of rho pi E rho C square root of 2 pi E rho C by Q into G V into Y heat affected zone, okay, plus 1 by T m minus T 0. What are all those terms I will just discuss. This is for generally you can say for line heat source, or you can say thin plate case. Okay. This is for thin plate case. Your peak temperature here T p is the peak temperature attained throughout a entire welding duration for a particular point. For a particular point, what is the peak temperature it achieved during its entire welding operation? That temperature, that is called peak temperature. Here I am writing. Okay. Now, for thick plate case, this peak temperature equation can be written as 1 by T p minus T 0, that equal to your 2 pi k alpha into E divided by Q into V 2 plus V into Y heat affected zone. What does it means? Every terms actually I will discuss, divided by 2 alpha plus 1 by T m minus T 0. Okay. So, what is T m? So, first one by one every terms I am discussing. What is this E? I have already written. E is the natural logarithmic exponent. Okay, that value is generally 2.7 to its constant value. T p is the peak temperature at a distance y from fusion boundary. This you should keep it in mind. So, y distance which we need to consider, that is generally the distance from weld zone boundary to perpendicular to that zone. Generally, let us consider this is your x axis, this is your y axis. So, there x, this is your y axis. So, you need to consider from fusion boundary to that point distance. So, first of all let us see, actually that I am just showing. Let us consider this is your weld zone, or you can say fusion boundary zone, this zone. So, for a particular distance from this fusion boundary, so this is the fusion boundary, this is weld central line, but the fusion boundary start from here, always you should keep it in mind. So, this is your fusion boundary, I am writing fusion boundary. What is fusion boundary? Fusion boundary is that line, you can say, or that locus at which your temperature goes up to melting point temperature. What I am telling, understand? So, this is the fusion boundary. So, from this fusion boundary at a distance, let us consider this is your y axis and this welding direction is x axis. So, this point, in this point you want to find out what is the, let point A, you want to find out what is the peak temperature. From fusion boundary to this distance is called Y has, heat affected zone. Okay. Always you should carry, it is not the measurement from center of weld line, you need to consider the distance from fusion boundary, that is why I have written Y has. Okay. Now, what is rho c? Rho is density of the material, c is a specific heat at constant pressure, g is the thickness of the plate, v is the welding speed. So, everything is known to you. Q is generally net heat input, eta V I. Tm, what is? Tm is the melting point temperature of the metal, whatever the material you are using, that is melting point temperature. All the unit is generally in Kelvin. You see T is generally capital letter I have written. So, T0 is the room temperature, or you can say if you use preheat temperature. So, T0 is generally called as initial temperature. This can be preheat temperature. So, from this equation you can get a very interesting types of relationship, both for 2-dimensional and 3-dimensional case, and for 2-dimensional 3-dimensional case you can find out throughout the entire weld plate what is the maximum temperature a particular point achieve, that you can easily predict. Now, what is the purpose of finding out fusion, what is the heat affected zone size of a particular welding process, what is the heat affected zone size, that things you can easily find. because you know I have already told you a little bit here also I am discussing. Let us in case of a welding process, let this is your weld bit. So, for any distance from this fusion, this is the fusion zone, let this is the fusion zone or fusion boundary. For any distance, what should be, any distance means this is your y axis. So, at any distance y from the fusion boundary, you can easily find out what is the peak temperature. So, by this generally what happens, if we know for a particular heat affected zone y value, what is your Tp value, peak temperature value, by the otherwise for a particular Tp value, what should be your y, that also you can easily calculate. Now, I have already told you generally heat affected zone is those zone which is generally zone from fusion boundary to recrystallization temperature 270 degree 73 degree centigrade temperature, let us for plain carbon steel, that is generally called recrystallization temperature, RC I am writing. So, from this, by using this equation, if you know all the parameter whatever in these equations are there, melting point temperature, E value, G value, V value, then by considering this Tp value you can easily find out what is your Y has, that means what is the heat affected zone size, what is the heat affected zone size, that means for a particular distance, let this dotted line I am representing, what is the heat affected zone width, that you can easily predict. What I am telling, understand. So, zone of heat affected zone you can easily predict with the help of this peak temperature equation. Now, from this equation you can get a very interesting idea, like what happens here, you can see this peak temperature you can say is directly proportional to, you can say is directly or linearly depends on your Q value. It is also this peak temperature also in case of 2 dimensional case, this peak temperature also you can say in case of 2 dimensional case this peak temperature is depends on, you can say your T initial value, what is the T initial value is there, it is also depends on that. How it is, that I am going to discuss little bit, okay. That I am going to discuss in next slide, little bit I will discuss, after that I will conclude today's lecture. So, from the above equation what are the things you can observe, that equation of peak temperature generally are useful for estimating what heat affected zone size, also for showing effect of preheat on heat affected zone. Preheat means T0. So, what you observe that this peak temperature 1 by T minus Tp minus T0 you can say is directly proportional to, you can say 1 by Q. Apart from these things you can see this T0 generally, if this T0 value increase, then what happens? It is also evident from the equation that all the parameter being constant, if preheat temperature increase, then you can say your has value, Y value will what? Y value will increase. How it is last that also I am just showing, because 1 minus T peak temperature minus T initial temperature, or you can say this is preheat temperature, this preheat temperature generally depends on what? Directly proportional to Y has. I have already shown in this previous equation, I have already shown. So, if this Ti value is increased, then what will be the things? Ti value increase means this bottom side things will be decrease, correct. So, bottom side things will be decrease, that means Ti increase, you can say Ti increase, then you can say Tp minus Ti this will decrease. So, if it is decrease, then your y has this distance will increase. So, you can say if preheat temperature increase, then your heat affected zone size increase. This you should keep it in mind. That things I have only written. Okay. Apart from these things, what we observe that generally this high intensity generally what is called power source give you a less heat affected zone. How it is little bit I am just discussing. Generally if this Q equal to you know this eta V I, high intensity beam means per unit volume how much heat is there or per unit area how much heat is coming. So, let us consider you are providing a heat by a small diameter arc and another diameter arc is little bit higher size. So, let us consider this is your A1 area cross section, this is your A2 cross section. This is let us consider for arc welding process and let this is for laser welding process, where generally you know laser welding is a spot very heat source is very small. Now, for a particular Q value, what is the intensity of heat or heat flux for this laser case? So, for this laser case you can say Q by A1 whatever the heat flux let us Q you are getting, that is let us watt per meter square. Then here for same Q value A2 as A2 is more, then here whatever the Q let this is your Q1 and Q2, this Q2 will be generally less. So, here you can say Q2 is much lesser than Q1, what I am telling understand. So, if your heat distribution, so you see, but for, so what I am showing you got the idea. So, if your size of the heat source will be more, then to get same intensity what are the things required, your heat input will be this Q value will be less. Like to make because what happens for melting purpose, let us for melting you need a heat flux value let us that is your Q. Okay. That Q you can get by what capital Q by A. So, for melting this much of heat flux is required both for what it is called laser welding as well as for arc welding. So, you see this Q value as in case of laser welding A1 is much smaller, A1 is much smaller than A2. That is why in case of laser welding process you can say this Q requirement will be less, correct, Q requirement will be less, Q will be less for laser welding where area is A1 to get same Q value. Whereas, for arc welding process where your volume is A2, area is A2, there generally to get a Q value your capital Q value should be higher, what I am telling understand. So, that is why here one word is written, high intensity process such as laser welding have a smaller heat affected zone. Why a smaller heat affected zone? Because it generally require Q value is less, a Q value generally is laser welding case is less than arc welding case. Now, I have already shown you this Tp is proportional to, you can say Tp is proportional to Q. So, if Q value is increased, then your peak temperature is increased, what I am telling understand. So, Q value increase, peak temperature increase. Apart from this thing I have already also shown this Tp is also, so higher the what is called Q value, then your peak temperature will be what is called higher. That is why here I have written a high intensity energy source result in lower total heat input, because the energy used in melting the metal is concentrated in a small region. So, that is why you should keep it in mind. Thus, high intensity process such as laser welding have a smaller heat affected zone. Why a smaller heat affected zone? You got the idea, because this Tp generally will be high for high Q value. Then what happens if high will be the Q value, then what happens, your Y also will be increased, heat affected zone size will be increased. If Q value will be decreased, then you see heat affected zone size will be decreased. So, these are the references which I have followed for this lecture. So, next class I will start from here. Next class I will discuss in details about preheating, then what it is called interpass heating temperature. Then also I will discuss about different types of heat treatment which are popularly used in welding process. Okay. So, apart from these things, if time permit, I will solve some problems in next lecture.